Okay, so today we will start with a new topic which is computers for robots, and this today's lecture is uploaded already, and the following students I want in front of the camera for asking questions. So please note down the names for those who have to come. So review of lecture 26, that was on different orientation representations were introduced, and then representations using single axis rotation was mentioned and described, and then the example using the single axis rotation representation was solved. For today we will be discussing the following topics: the introduction of what the computers used in robotics, then talking about the use of computers as a controller, how to improve the speed, the computer speed. One could be based on the software approach, what can you do in the software and what you can do with the hardware. So both approaches will be discussed. Then hardware requirements, how the hardware in a computers are organized to control a robot. Then the control considerations, when you control a robot, then what are the aspects a controller has to take into account. These control considerations are different than the robot control. In a sense, the controller, other than those PID control to achieve the motion, there are other issues. So those issues will be discussed here. And finally, the robot programming, that means how the user interface is with the robot hardware. So different programming languages will be discussed, and finally the summary of today's presentation. So in the introductions we see that we have so far done lot of calculations. We have done kinematics. So we have done kinematics, where we have related the end effector positions with respect to the joint positions. We have done the dynamics, that means to calculate the joint torques required. We have talked about control calculations, where PID gains are multiplied with the errors. So they all require complex computations. If you remember your kinematic or dynamic calculations, there are a lot of sine functions, cos functions, tan functions, right. So they are all complex calculations, including trigonometric functions, okay, which I just mentioned. So we need lot of complex computations to be able to control a robot. Now many of these calculations need to be done in real time. Okay, what do you mean by real time? Now if a speed of the robot is say 1 meter per second, okay, but if your calculations to reach from one position to another position takes more than few seconds, then obviously you cannot achieve 1 meter per second speed, because to reach 1 meter from one position, look at my hand here, say 0.5 meter per second. So from here to here is 0.5. So 0.5 meter per second, if it has to reach, now this will go to several steps of calculations, right, as per our trajectory planning. So now to go from here to here, which will be say 0.01 meter, if this itself takes more than a minute, so this will be waiting here and it will take a second, it will go there. Then it takes more than 1 second, it goes there. So it takes more than 1 second, it goes there. It takes more than 1 second, it goes there. So if I want to go 0.1 from here to here, 0.1 meter, and if it goes at the step of 0.01, and if each step takes about 1 second, so 10 steps takes 10 seconds to go to from this point to this point, 0.1 second in 10 seconds. But you want to run the robot in 0.1 meter per second, not in 10 seconds. Okay. So, obviously, we will not be able to go that fast, we will go this. So, what I mean is, so this time taken from here to here should be, if this is the speed I want, so then my computational speed should be much faster, so that it can go from this time to this here. So, it should be able to compute that fast. Okay. So, I repeat, so if I want to reach 0.1 meter from here to here in 1 second, so my computation should be done in much less than 1 second, so that I can go step by step and can reach there. So, that is mean as a real time. Okay. If computational speed from here to here is say 10 seconds, so that is the limitation of my speed of the robot. So, 0.1 second per 10 second, in other words, is 1 meter per second. So, that is 10 centimeter per second will be the speed. Okay. So, the speed of the robot will be limited by the speed of computations done by the controller. So, in many existing robots, so that is I am writing here. So, many of these calculations need to be done in real time, that is, they must be completed within a very small time period, okay, say about 15 milliseconds. Okay. That means, all 6 joint motions should be known to the controller in mode in 15 milliseconds. Okay. Then only you can able to approach the speed. So, computational speed, as I read, should be less than the ability of the robot's speed, which I have just explained with my hand. Now, talking of the computational speed now, how to increase the computational speed? Now, there are ways to reduce the time, for complex calculations. Let us see how we can do it. As I said, one way is to the software speed up, that means we can increase the efficiency of my software. Okay. Now, the techniques to increase the speed of computations in a conventional computer, how it can be done? These techniques take advantages of unique properties of many calculations. Okay. So, just like one example I might have told you when I was with you there. For example, if you want to calculate a square, let me show you this calculation on the paper. Suppose you want to do this calculation, right, a square plus 2ab plus b square. So, this requires 1 multiplications, this requires 1 multiplication between 2 and a, and between a and b another multiplications, this requires 1 multiplications, this requires 1 addition, this requires 1 addition. So, total now multiplication 1, 2, 3, 4, 4 multiplication and 2 addition. Okay. Now, instead if I know that this is a plus b square, so I need 1 addition here, and for the square I need 1 multiplication. So, instead I need 1 multiplication and 1 addition. So, this is the way I am efficient. So, this is more efficient. Okay. So, this is what I meant as taking advantages of many calculations. So, here if I know this is expansion of this, so then I can take the advantage. So, these are the ways one can take advantage of different expressions and reduce the computation time. So, go back to the slide. So, one of them is use integer arithmetic. Okay. Numbers will be represented as integers and avoid the using of floating point representations. Suppose if I have a value 22.75. Okay. So, what I will do is I will not do the calculation is 22.75, I will do the calculation is 2275. Okay. And then later on whatever results come I will divide it by 100, because I have taken a scale factor of 100. in order to make 22.75 as an integer number. So, a mixed number, for example 22.75 is represented by an integer number, that is 2275 multiplied, or what we call as a scale, by a constant 1 by 100. So, suppose if I have to do these calculations, say go to the page again, 22.75 plus 3.54 plus 7.81. So, I will say that okay, these are all scale. So, I will just add the integer numbers and later on I will divide it by 100. So, computer will do these calculations. Computer performs this very fast. Okay. So, computer will do this thing, and at the end I know this is just 2 digits later. Okay. Whatever results I come, so I know this will be 1 digit here and 1 digit here. Okay. So, this will be my dot here. Okay. So, for the computer I will do these things, and later on I will say okay, the exact values are corresponding to this, and some scaling I will do it somewhere. So, that is the way I can improve the speed. So, go back to the slide. If the scaling is constant, considerable speed advantages can be obtained over floating point. Floating point means with the decimals. Integer arithmetic is typically 5 to 10 times as fast as floating point one. Okay. However, there is a little bit loss of accuracy, because if you multiply 22.75 by some number, say 3.14, then obviously its numbers may be something digit, and maybe accuracy wise there may be more digits coming here. But since I am scaled by 100, so computer is taking only these 2 digits. Okay. So, if these 2 digits is say 2 and 8, or rather let us say 9, 2 and 8. So, what I mean is I have a data something 0.28, okay, say 2, 8, and the next one is 9. Okay. So, I know this is close to 0.29, but my computer will take it as a 2.8. So, the accuracy, this accuracy will be affected. So, I repeat what I mean. If you do the calculation in integer number 22.75, 3.14, if the result is something 0.289, okay, so computer is calculating it as a 0.28. However, in true spirit it should be close to 0.29. Okay. So, this is the meaning of loss of accuracy is inherent. Now, that is for floating point number, okay, or the real numbers. What about trigonometric functions? Okay. So, this is algebraic calculations here, and this is for trigonometric calculation. If you look at our commercial computer, like the laptop you have or the desktop you have in the laboratories, in commercial computing system, trigonometric functions are evaluated by several techniques. Okay. One of the techniques is called the rational functions. Okay. Another is called the Chebyshev polynomials. Okay. Or these rational functions, Chebyshev polynomial, or you see any function sin theta can be calculated as theta plus theta square over factorial 2 plus theta cube over factorial 3. Now, all those values you know. So, they are series expansions, those calculations are done. Okay. And you can imagine in those series expansions, if you even take up to 10 numbers, it will become very complex. So, and then in addition, if you do the arithmetics in floating point, even though it will lead to very high accurate results, but the speed will be very low. Okay. So, what is done here is in computer, in robot, I do the speed fast because that is very important aspects for me. Accuracy I lose little bit, but then I take into account through my control. This less accuracy I can consider as a disturbance for which the robot cannot reach to the appropriate positions, but that I can take care of through my control gains. So, that is in robotic applications the most appropriate mechanism for trigonometric function is a lookup table. Okay. So, let me demonstrate with my paper here. So, a sin theta can be given as this expanded form. So, this long time slow but accurate. Okay. So, because the speed is very slow which I want to increase, so what I do is I make a table like this, and then I go theta versus sin theta. So, theta 0 is 1, no? Then I calculate 0.1, I calculate this value, 0.2, I calculate this value. So, a robot will check what is the value you want. If you want at 0 degree, I find out this. So, this is called lookup table to speed up the calculation. Okay. But suppose if you need a value in between 0.05, 0.05, then this data is not available here. So, what do you do for that case? Okay. So, that is explained next. So, for example, values of sin theta are simply stored in a table for theta equal to 0, 1, 2, 3, 89 degrees, something like that. The table for 90 watts provides instantly the value of sin at an angle of 1 degree precisions. In fact, 90 watts require less memory than the required by a program to compute the function explicitly. Okay. Then in high accuracy, then the nearest degree is required, two options exist. As I was going to tell you, if you need a value between 0 and 0.1, on my screen it is 0 and 1 degree, then you have two options. First is a linear interpolations. Okay. And so, first is the linear interpolation. What is linear interpolations? You must be knowing it, but just to confirm, let me briefly explain you. So, in a lookup table you have theta and sin theta. I go back to what I have written in the presentation. So, sin theta is 0, 1 degree value, 2 degree value. So, if I now want a value at 0.5, so I do linear interpolations, means I say okay, this is my theta value and this is my sin theta. Okay. So, I have theta equal to 0, I have this 0, and then 0.1, 0.1, I have some value here. So, linear interpolation means I join them in a straight line. So, if you do it at 0.5, I do. So, a sine curve is like this. Okay. So, this I know as 90 degree, sorry, this is 180 degree, so this is 90 degree. Okay. So, this you have divided into small 90. So, this is 1 and this is 89 and 90. So, each segment I considered is a straight line. Okay. So, between 0 and 1 degree, that means 0 here and this is 1. So, between this I consider it as a straight line, and if I need any value in between 0.5 or 0.25, I consider it as a straight line, okay, which has a value of now y equal to mx plus c, and then I can calculate. Okay. So, this sin theta, say this is y. So, y is equal to whatever you have this value, no. So, this value is y at 1. So, y at 1 minus 0 over 1. So, then at any point of time, so your functions will be this y1 t, that is it. Okay. So, this is called linear interpolation. Okay. If you need between 1 and 2, then you plot, okay, for 1 I have this much value and 2 I have this much value. So, this is 1 and 2. So, now you calculate a straight line between these and you calculate for the interpolated value. Okay. So, that way between every interval there is a straight line, between this interval another straight line, between this another straight line, and then you can calculate if there is any value demanded in between. So, next is another type of interpolations. Okay. So, as I said, the first one is the linear interpolation, which is done here, and the second one makes use of trigonometric identity. Okay. So, here I take care of trigonometric identity for the same sine of two summed angle. Now, suppose I want to calculate value of let us say 0.8034. Okay. So, what I have, the value what I have angle I divide into two parts. Okay. And then I know the sin alpha plus beta is equal to sin alpha cos beta and plus cos alpha sin beta, right. Then what I do is, the angle is the segmented two parts, an integer and a fraction. Okay. Integer and fraction. So, exact evaluation require 4 lookup tables. Okay. And that I am going to show you how it requires a 4 lookup tables. Then approximate evaluation can be obtained even faster. Okay. For this, the angle is scaled so that the fractional part is very small. So, like for example, if cos beta is 1 and sin beta is equal to beta, right. So, we will see how it is done. Now, there is an example here. Assume that the values of sine functions are tabulated, okay, at an interval of 0.01 radian increments. That is, values of sine 0.8 and 0.81 etc. are known. So, now if I want to calculate 0.8034, so I divide into two parts. One is sine 0.8, so sine 0.80, so sine A cos B and then cos A sin B, right. Now, cos small value is approximately equal to 1 and then sin this value is equal to 0.0034. So, this result requires what? For the very small angle 0.0034 radian, cos 0034 is 1 and sin 0034 is 0.0034, right. So, now the final result is sin 0.8034 is equal to sin 0.80 plus 0.0034 into cos 0.8, right. So, now what you require is sin 0.8 and cos 0.8 are available from the lookup table. So, this interpolation technique requires two table lookups. That means, you have to see the value of sin 0.8 and cos 0.8, one multiplication here, okay, and then one addition. So, you have to look for two values, one multiplication and one addition. Okay. But whereas if you follow directly this approach, that means sin alpha cos beta cos alpha sin beta, no, then you require exact evaluation requires 4 table lookups, because you have to see the values for sin alpha from the lookup table, cos beta from the lookup table, cos alpha from the lookup table, sin beta from the lookup table, okay, and then multiply and add. But for a fractional number, we have seen how it can be simplified. So, these are different ways to increase the speed of computation. Now, look at matrix operations. So, what I have told about the scalar operations. So, in this lecture, I am giving some of the outlines of how things can be improved. In real life, when you have to do the real programming, you have to see how these things can be applied, okay, or similar methods can be adopted. In matrix computation, in robot control, we have matrix inversion. Many cases we require 1 minute, there is a mistake here. Okay. In robot control, explicit matrix inversion is generally not required, but suppose if it is required in some cases, because in Jacobian inversion is required sometime. So, a set of linear algebraic equations are solved. Okay. How, I will explain you soon on the paper. In like for example, go to the paper now. Suppose I have T E is equal to j theta dot. Okay. So, I am talking about our velocity expressions. So, if you want to calculate theta dot is j inverse T E, what is told just now is explicit inversion is not required as its calculation is expensive. So, how do you do it? We do it in following manner. Suppose T E x, T E 1, T E 2, T E 3. Now, suppose if I have these 3 values, and then you have j 1 1, j 1 2, j 1 3, j 2 1, j 2 2 and j 2 3, j 3 1, j 3 2 and j 3 3, and then you have theta 1 dot, theta 2 dot and theta 3 dot. What you do is you do what we call as a Gaussian eliminations, okay, which will change, okay, it will make it in a upper triangular from 0 0 0, no, and then theta 1 dot, theta 2 dot, theta 3 dot. What I am telling is basically use method of solution for linear algebraic equations. So, what I am telling is instead of using the explicit inversion, you use a method of solution, and the method is something like this. You do the Gaussian elimination, do the upper triangular form, and then you do the what we call it is a back substitutions. So, these are the words I am writing it here. If you want to revise, you can go back to your matrix computation books, and you can see how a linear equations in this form can be solved in these manners without finding out the inverse. So, that is my intention of this statement. Now, suppose there may be a situation where you need to calculate the inverse. maybe this is not that you want to find out theta dot, but you need inverse. So, how to do it? There also we will use the same method, and this we have done during my lecture in Addis Ababa. Suppose I need J inverse and I say this is equal to x. So, x has x 1 1, x 2 1, x 2 3, x 3 1, x 3 x 1 2, x 2 2, x 3 2, x 1 3, x 2 3 and x 3 3. So, if J inverse is x, then I know J inverse x is equal to identity matrix which has 1 0 0 0 1 0 0 0 1. So, in this case I know that J 1 1, J 1 2, J 1 3, J 2 1, J 2 2, J 2 3, then J 3 1, J 3 2 and J 3 3 into x 1 1, x 2 1, x 2 3 is equal to 1 0 0, because when I multiplied with this matrix and this vector here, it should be giving the first one. If you multiply this in x 1 2, x 2 2 and x 3 2, you will get 0 1 0. So, this thing gets multiplied. Okay. And then similarly here x 1 3, x 2 3, x 3 3 will be 0 0 1. And once you bring to this form, you can use method of solution for linear algebraic equation, and you do it once, twice, thrice, okay, 3 times will give inverse of J. So, if I need an explicit inversion of this matrix J, I can write in this following manner and can use the method of linear algebraic equations to get the inversion. This is much cheaper, much faster than definition of adjoint etc. Because J inverse I know it is adjoint over determinant, no, and this will be much faster than these adjoint definitions. So, this is the thing now I will be showing you on the screen, that if an explicit inversion must be computed, it is done numerically by solving a series of linear algebraic equations whose right hand sides are the columns of an identity matrix, whereas the corresponding unknowns are the columns of the desired inverse, and that is the same thing here. So, the columns of my inverse, columns of the unknown inverse elements are the columns of unknowns which I will be calculating, whereas the right hand side are the columns of the identity matrix which will be forming this one. Okay. So, this is the method will be used for matrix operation, and the same thing I have written on my screen here, that if x is the inverse of an n by n matrix J, that is x equal to J inverse, then I can solve J x equal to 1 n times, and this is the solution which I have written there on the paper also. So, J x I is the column of this matrix here is equal to E I, and E I is nothing but that 1 0 0 0 0 0 1 0 0 0 1 time. So, this is the formal way of presenting what I have written there. Now, the question is accuracy versus speed, which is more important for us. For us, robotics control, it is the speed which is more important. However, if we are talking about numerical analysis just in calculation, it is the accuracy which is more important. So, in this robot control, our intention would be to look for the speed, and some of the methods are already explained to you. Those are the software approach to reduce the speed, to increase the speed. Now, how we can do in hardware? Okay. So, some hardware considerations. So, we talk about distributed computing. Instead of having one computer to control the all 6 axes of a robot, we can think of 6 different computers controlling the 6 different motion, but then to have a coordination between them, you may require a supervisory computer. This kind of system we call it distributed computing. That means the use of several computers interacting in real time to provide the required computational speed. If you cannot have 6, let us have 3, maybe one computer will 2 joints each, but they should be able to communicate with each other so that they know what is happening. Now, example of distributed activities can be, say, reading the encoders for position information. So, maybe one computer might be devoted for reading the encoder reading for the position informations of all the joints. Another could be computation of the joint servo error signals for the control aspects. Now, here I will show you an example of a Puma architecture. So, here I am saying that for joint 1 I have one microprocessor BUP, joint 2 I have another microprocessor, joint 3 I have another microprocessor, joint 4 I have another microprocessor, joint 5 I have another microprocessor, and joint 6 I have another microprocessor, and all of them are supervised by these large scale integrations, another device here, which is keeping connection between all 6. So, a separate processor is attached to the input and output transducer of each joint. This processor maintains current information of that joint. Central processor, that LSI 11, reads the joint processors, computes the kinematic transformations, and provide the set point to the joint processor. So, this keeps the local current information, then this knows what is happening here, does all these mathematical calculations and sends them that how much more to move, how much more to move, how much more to move, and so on and so forth. But this kind of architectures, we call it architecture, is sometimes is not advisable. Okay. So, alternative architectural philosophy of computation is distribution by function. So, here we have distributions by joint, but instead we can have a distribution by functions. Here I have an architecture. Oops, no, this is not the one. Okay. Yeah. So, distribution by function here. So, maybe this 9900 is for making all these joint informations, and so and then its computation should be done by, so 9900 to 9511, whatever may be the processors I have, this indicates a processor, microprocessor. It will do all the necessary calculations for this joint, this will do all the calculations for this joint, and so on and so forth. Obviously, method to calculate in such style needs to be little different, and whatever the informations are coming, they will be kept as a global memory, and that information will be shared by others. So, each processor maintains the position and velocity of its joint as well as the various trigonometric functions of those parameters. These quantities are stored in multi-ported memory and hence are immediately available to the other processors. So, this global memory is called the multi-ported memory, and which is accessible to all the joints. Sometimes there is a combination between these two also. This scheme distributes the computational burden uniformly at the expense of a complex hardware and more complex software. Because as you see, if each joint has to know that what is his inverse kinematics, which is difficult. So, an immediate improvement of this architecture is to disassociate the servo calculation from the kinematics. The PUMA architecture with single central processor replaced by an array of processor for common memory. So, which is no. So, now here you see only each is things are done, but here now this is for the proposed architecture for the decoupled servo calculation. So, very similar to the previous one, but I have put a separate processors also with it. Okay. So, these things are done and the servo controllers are done. So, basically this philosophy applied to PUMA robot and which is illustrated here. So, these are my hardware requirements. So, basically hardware it says trying to distribute the computation to different computations. Okay. Either you do it information locally, central calculations, or information and calculations locally. So, these are the two philosophy we have seen it. Now, the hardware which you use for control purposes other than calculations, it has to have several other abilities. Now, these abilities now I am pointing it here. The control system should be supervising the following abilities: capability of moving objects, that means manipulative ability. It should be having the ability to know the sensor information, so we call it sensory ability. It should have the ability to modify the behavior in a pre-programmed way, that is the control laws. It should have the intelligent behavior abilities, ability to store, elaborate and provide data on system activities is data processing abilities. So, to achieve this, we can have effective implementation is done using a functional architecture. So, to achieve these aspects, we can have what we call the hierarchical approach. In the hierarchical approach, it is very similar to the military approach, where the general pass the orders to officers, then officers pass orders to the sergeants, and sergeants pass order to the troops. So, the actions orders go there in this fashion, and then what is happening there, the information will flow above. So, flow down from the top and reporting back to the up. Okay. So, that is the way this information is exchanged. To show how this is done, there is a block diagram here. So, this is a program module prepares task description table. So, this is done by the programmer, then it tries to enter the control module, this dotted line. Okay. The interface of task description commands in the control system, and this location module will have the descriptions of the location. For example, move is a command. So, here I make a task move 500, but what is the meaning of move in machine language is kept here. So, there it takes the meaning of this thing and does the actual calculations, and whatever results are coming 1.0, 2.0 etc., they are stored in the database, and then finally it goes to the computer. Remember, this is the programming aspects. After that, there are other hardwares. For example, for the motors you will have the amplifier and all those things, driver circuits, which we have discussed during the motor studies. So, now who will do this communication, for which we need the robot programming. Okay. And this is one of the greatest advantage of using robot, because we can use a program to control. So, greatest advantage in industrial application of robots is their flexibility, ability to rearrange for new production, and large area coverage of movement. Okay. So, major obstacle in using manipulator as a general purpose assembly machine is the lack of suitable and efficient communication between the user and the robotic system. So, which we are talking basically about the programming aspect of it. So, utilization of the robot's flexibility presupposes effective programming. So, we presume that you do a good programming. Okay. Now, there are several ways to do the programming. Two of them are mainly classified as online programming and offline programming. Okay. So, in online programming, it takes place at the site of the production itself. It has a teach pendant. If you go to your laboratory downstairs, you will be able to see your robot has a teach pendant. So, you move the robot using teach pendant to an object where it will be picked up, you take it to another location, place it there. So, you have taught the robot from going to point A to point B, you record whatever you have moved it and you replay it when you are not there. So, this is the activity for online programming. So, it has certain advantages, it is easy accessible now in coordination with the actual positions which you can see, simplicity in programming because you are not doing any handwritten programming, you are just moving using the teach pendant. Of course, disadvantages are slow movement while the robot is programmed. So, program logic and calculations are hard to program. Okay. So, look at my hand to understand this concept better. Suppose this is my robot and this is my teach pendant. So, I say okay, joint axis move by, I am pressing the button here. So, it moves, then I go to the second button, joint axis 2 moves, then I go to the third button, no, it moves, then I pick up from here, then I say gripper open, gripper opens, okay, gripper close, gripper close. So, I have now taken the object, now I press joint 3, okay, joint 2, and then joint 1, gripper release, gripper release. So, whatever I have done now, if I can record it and then I say replay, so it will go pick up place, go pick up place, right. But notice that the process when I am doing programming, I was doing it very slowly and so that no activity can be done because I need the robot to do the programming. Okay. Moreover, when I was doing it very slowly, when I have released it and gripped it, no, I was moving it very slowly, but in actual operation it will be done very fast. So, while I am taking it very fast, the object may fly away from there. So, it is difficult to predict that how much grip force I should apply, so that when I replay my motion with high speed, it should not fly away. So, these are the some of the disadvantage which is mentioned here. So, here again we can classify as a lead through programming. Okay. That means you guide and playback the way I have said it, and we say walk through programming. Okay. Walk through programming is like this. Again, look at my hand. Suppose lead through is I go slowly to every points. Walk through is I take the points here and I take to the next point. Okay. These 2 points here and here I do not teach anything, those calculations I will do using a program. Okay. So, lead through is every point I teach, okay. But walk through is I teach here, rest I do the calculation. So, it is a combinations between the lead through and some computations. Now, one of the major disadvantages online programming is that you are keeping your robot engaged, which is not good for the productivity purposes. So, there are something called as offline programming, that means you do the computer programming of robot on the computer screen itself. So, it takes place on the computer and the models with the work cells with the robots. Okay. These robot programs can in most cases be created and reused exist in the CAD data. Okay. I will show you one such scenario. Okay, let me go to my you see in this screen what you are seeing is actually offline programming is done. Okay. For these robots, whatever operation will be happening. No? So, this is a CAD environment in real time. Now, you see the robots are moving here. So, these movements I can do in my CAD environment the way it is shown here. So, once this moves perfectly all right, so then these programs I will save it and download to the real robot, and then real robot will be played back. Okay. So, this what is happening here is a simulation. Okay. This is one type of offline programming, that means programming by simulation, which is the third type which I will be discussing on my slides. Let us stop here. So, this is the I go, let us move. Okay. So, advantage of offline programming, it does not occupy the production equipment, effective programming with the logics and calculations with state of the debugging facilities, and so on and so forth, which you can read yourself. No, effective programming of location, but it has certain disadvantages. Now, as you have understood from that simulation, it requires a very expert users. You have to have a CAD knowledge, you have to have a good programming knowledge, and all these computers have to be bought for performing the offline programming. So, these are the features should be implemented in the offline program. For example, world model needs to be done, as you have seen in that animation, motion control has to be provided, error detection capability has to be provided. So, in simple words, your ability of CAD, computer aided design and animation has to be very good. So, the example, then the next one. So, this was in offline programming, one is doing the CAD modeling. Then what we call is the robot oriented programming, right. So, an assembly task is assembly described by a sequence of motions. So, instead of taking it to one point to another point, in this advantages offline programming, offline takes place. Okay. So, this has been actually misplaced here. This is an example of a robot oriented programming. An assembly task is explicitly described as a sequence of robot motions. The robot is guided and controlled by the program throughout the entire task, with each statement of the program roughly corresponding to one action of the robot. Okay. So, this is, suppose this is the task I have to do it, that I have to pick up an object from here, and then I have to pick up an object from here and place it here. This is actually came to the wrong place. Robot oriented programming. This is one of the, okay. So, in offline programming, the two types of hierarchy, these two types I have given you the concept. So, one is called the robot oriented programming and another is the task level programming. In the oriented programming, here you define the base, you define the beam and define the feeder. In AL is one language for robot programming. How they are defined, this is a nomenclature for that language. Just like our C programming language or Fortran programming language, so they have their own language, and that is the way they have done the programming. So, in task level programming, you define in terms of task, not in terms of motions. So, this is the way the task is to pick and place, how many different motion will there are. Pick may be one motion, one task, place may be another task, hold may be another task. So, then the subtask planner will divide this thing, and taking the kinematic information, it will do all these calculations and then perform the motion. And this is the last one, is called the programming by simulation. So, here you will have a window. So, now this is one robot. So, you move by waist angle here, no shoulder angle. So, you move by which amount you want to move, the robot will move to different positions, and then if you are happy, then you say okay, I am happy, done. So, now it can be downloaded to the real system. So, with this I summarize different aspects of computer uses in robotics were highlighted. Software requirements are mentioned, hardware requirements are also explained, and robot programmings are defined. So, in this lecture I have not explicitly talked about any particular programming languages, because different companies will use different programming languages. So, there is no point in understanding a particular language. Furthermore, in a course where we wanted to learn a general aspects of robots, so I found it is not necessary to teach you a particular language. When you use your own robot in your laboratory, that robot will have its own language. So, anything you want to control with your robot, the same language has to be used. So, if there are quick questions, general questions, you ask, otherwise these 8 students will come in the front and we will have interactions.
Thanks. No questions.
Okay, so please, Ato Demeke was absent in the last class. Demeke Abu Said, raise your hand. Okay, Mese Alemu, raise your hand. Then Nestanet Desalegn, please take your seat quickly, we have 5 more minutes. Samson Zerihun, okay, Ato Sisse Amare, Tesfaye Abreha, okay, come in the first bench. Tesfaye Demelash, I can see you, Tesfaye Demelash and Tesfaye Molalen. Okay. So, we will start. Please ask, or I will start asking. Yes.
Hello.
Yes, yes, I can hear you.
I am Samsul. And my question is from today's lecture,
Okay.
programming, online programming and offline programming.
Right.
Said about the and can we design the display by ourselves, or can we buy from other companies?
The company who makes robot, they also supply the programming language.
What about the display that?
Teach pendant is for online programming. Okay, that also requires a software to communicate between the teach pendant and the robot. Suppose you have a move 500, so you press a move button and then 500 button. So, the move, the corresponding meaning of move is sitting in the computer here, and that goes to the robot there. So that kind of programming environment, okay, or rather controlling environment is provided by the company. We do not do anything. We just press move, go, come, raise, release. So we just keep on pressing. Those are part of programming languages developed by the company.
Okay. And then another question is, which basic robots have Hello workspace?
Please,
It is Hello by Hello.
please repeat.
Which basic robots have Hello workspace?
Okay, which basic robot has hollow workspace? Which one? We have to go back to this thing. Huh? So I think cylindrical robot will have a hollow. Whichever robot which you see, this is the gripper. The cylindrical robot, if you cannot go more than certain distance, because hollow workspace, one of the simplest one is, if this thing cannot reach to this space, right, you will create a hollow. For example, cylindrical robot, it can go up and down, it can go sliding close and far. So, but close is how close? It cannot go to my axis. So, it can go up to this much. So, those means it will, so this much create, it will have a hollow workspace. Let me just try to bring out my presentations. I think it will be clear. So, I think it was in introductory class, maybe this thing, classifications. Okay, here. Here you can see that this cylindrical space will be hollow space here, right? Let us see if I can go to, okay, here you can see cylindrical, this portion is hollow here, okay, because the end effector cannot go to the extreme positions, okay. The same here, it can go, it is hollow here, and here it is not very clear, but some portions will be hollow. It will not be hollow at the center, it can have hollowness inside also. So, articulated robot can have hollow some other places than at the center, whereas the spherical and cylindrical have hollow only at the central zone. Okay. Next.
Hello, sir.
Yes.
When to use a computer for controlling, what type of software used in computers?
For controlling the robot?
We use a computer.
Yes.
Then what type of software we use?
Okay. For, you see, again it is dedicated to the company. So, company decides, but if we want to control a robot, there are several softwares but is available these days. There is a LabVIEW is one software which can be used to communicate with any hardware and any computer. MATLAB you can do it. There is something called DSpace. No? These are all general purpose software which can connect with the computer and the hardware, but a robot manufactured by any company will have a dedicated software specially built for them. Okay.
Oh,
Okay. I will take as last questions. No questions, others are not asking questions. Huh? Maybe next time I will ask specifically questions for them. Huh? Okay, since it is 1 past, so let us stop here, and tomorrow hopefully will be our last lecture class. It will be on robot applications. Okay. So, there will be lot of videos and a lot of photos. So, please do not miss tomorrow's class. Okay. Thank you.
okay. Hello, sir.
Yes.
Hello.
Yes, yes.
I asked something about the mid exam for you.
You ask for?
I am Yosef.
Yes, yes. What did you ask?
La, la, yeah, last time you showed
the exam paper for other students.
Not other students,
that time I
only
was absent.
only 4 or 5 students who had a complaint about the marks. I have showed their paper.
Okay. I
You have a complaint?
on that time I was absent. On that time I was absent. If you bring it, I want to see.
You can send me email, otherwise I will not remember.
Okay. Okay.
Okay, bye.